All right, good morning. Again, I will have the test one available later today at 12. And again, the deadline for submission will be Monday at 11:59 p.m. And just sort of resuming what we have with the first test review. And we have from page 115. And for the case, we have in number 90. Okay, we have for what we have here. Okay, so you have 10 times w to the 2/3 is equal to 1/10. Okay, so here we have an equation, and we're looking at solving for w, and we have w is given as being raised to a non-integer power, and we're going to be looking at converting what we have in w to the 2/3 into its radical equivalent. Okay, so you have again the nth root of a to the m, okay, is the same as saying what we have for a raised to the m over n. Okay, so and for what we have in the case of w to the 2/3, if I were to rewrite this in radical terms, okay, so the type of root is indicated by the denominator. Okay, so we have the cubic root of w raised to the second. All right, so for what we have in this equation, okay, so I'm going to isolate w to the 2/3 upon division. Okay, so you have 10w to the 2/3 over 10. Okay, we have is equal to 1/10 divided by 10. Okay, so left hand side, okay, we will have it w to the 2/3. And for what I have to the right, 1/10 divided by 10. Again, if you're dividing by a number, it's the same as multiplying by the number's reciprocal. Okay, so we have w to the 2/3. Again, it's going to be 1/10 of itself. So we have w to the 2/3, okay, is equal to 1 over 100. And now, rewriting what we have in w in radical terms. Okay, so we have what is going to be, once again, the cubic root of w squared is equal to 1 over 100. And now, shifting gears a bit, okay, so I'm going to get out of the cubic root, okay, and free up w squared upon taking both sides and cubing. And so for what we will have here, okay, so we will have w squared, and for 1 over 100 times itself, we already have a small fraction to begin with. And this fraction is about to get much smaller, relatively speaking. In fact, you have 1 over a million. And now in terms of the follow through, okay, in terms of configuring, okay, what w is going to be, okay, now with the square root property of equality, again, you have like x squared is equal to p, and then we have going to x is plus or minus the square root of p. So we have x represented by w, p by 1 over a million. And as I go from w squared to w, okay, so you have plus or minus, okay, the square root of 1 over a million. And the thing about the denominator, 1 million, not only is it a perfect cube, but it is also a perfect square. And in this particular case, right, so we have w's plus or minus. Now the square root of 1 is 1, and the square root of 1 million is going to be 1,000. So we have for w, we have additive inverse solutions. Okay, in the case of the small fractions, which we have with positive and negative 1 over 1,000. All right. Now, in the case of the next item, okay, and we have just writing equations in terms of a specified variable. Okay, and this is a bit of an outlier section, and it sort of overlaps, okay, with chapter 1. And part of it is, okay, again, writing or converting equations in terms of a specified variable. And for 91, okay, we have a linear equation with terms in the letters x and y, and we have the standard form of a linear equation where we have 4x minus 3y is equal to 6. Now you're looking at expressing this equation in terms of y equals, and this kind of conversion, you're looking at going from standard form to what is going to be the slope-intercept form of a linear equation. Bit of a future topic. So we have 4x minus 3y is equal to 6. And if I get the y term by itself, right now, we have the y term at negative 3y. And so if I proceed by taking 4x away from both sides, so we have negative 3y is equal to, you could say either 6 minus 4x, but if I'm looking at creating, a pathway to what's going to be regarded as the slope-intercept form, you're going to have the x term in front of the constant. So right now we have negative 3y is equal to negative 4x plus 6. And if I divide everything out by negative 3, so what we are going to have here, the left-hand side becomes y for minus 4x over minus 3. Okay, now the negatives will cancel each other. So this will become 4/3 of x. And for 6 over negative 3, okay, we come out to minus 2. So we have in this end result, okay, we have that y is equal to 4/3 of x minus 2. And now, 96 is a bit of an outlier. And this one, kind of a big challenge in a way, because you're looking at writing the equation involved in terms of a variable directly or in direct fashion, while that variable is a fractional denominator. Okay, and here we have 1 over a is equal to 1 over b plus 1 over c. And we're looking at writing this equation in terms of b equals. And if you notice the case, what b is in the denominator, how do I go from 1 over b to b equals? Okay, what you want to do is that, okay, you don't want to take the reciprocal of everything and have like a is equal to b plus c. You don't do that. What you're going to have to do instead is to eliminate a, b, and c, multiplying everything out by the least common denominator. Okay, so we have for LCD, we have a times b times c. And if I distribute the LCD over all the terms, okay, so I have ABC all over 1 over A. Then I have ABC times 1 over B and we have plus ABC times 1 over C. I'm going to repeat this just to show the cancellation process. Okay, so for ABC times 1 over A, we could look at this through cross multiplying. Okay, so you have ABC times 1 over A. So you have like ABC divided by A, so you're going to have A's to cancel. For ABC times 1 over B, think of it like ABC over B. You're going to have the B's to cancel. And for ABC times 1 over C, which would be ABC over C, we have, upon simplifying, okay, we're going to have the C to cancel. And for what is left standing, so you have BC is equal to, and you have AC, and we have plus AB. Now we're looking at expressing this equation in terms of B equals, and we have 2 out of the 3 terms left standing to consist of the letter B. Okay, so I got for the term on the left with the letter B, it is by itself multiplying C, and I can join this with AB. So I can move the AB term over by subtracting. And for what we have here, we have BC minus AB is equal to AC. So I now have a couple of B terms that are given in direct fashion, and to consolidate as a single B expression. Okay, what I can do here is that for this difference, I can factor out B, and B will go into BC minus AB, C minus A times. Then we have in the follow through, just getting B by itself. So I can divide both sides by the binomial C minus A. And so we have for the end result on this one, okay, we're going to have that B is equal to AC all over C minus A. All right. Now, so just looking at what we have again. So again, I had this fraction where or I should say the fraction 1 over B, and had kind of go through a circuitous route to get in everything in terms of ultimately where I could get it expressed along the lines of B equals. So I applied the least common denominator and canceled out the fractions, and so I was able to get, with some rearranging, combining like terms in the follow through, I was able to factor and get B by itself, and so we had that B is equal to AC all over C minus A. Now, for what we have in the case of the next set of items, and we have once again with essentially the complex number system, and we have with the following group. Okay, so in the case of number 104, okay, so we have an equation in terms of the variable t, and we have 10t squared plus 1210 is equal to 0. Now I could technically divide the equation by 10 and just write this as t squared plus 121 is equal to 0. That is one approach upon which you could initiate the problem solving process. Or you could just divide later, and we can do this if we isolate 10t squared, where that is going to be equal to minus 1210 and then we have upon dividing by 10. So you have 10t squared over 10. Okay, so you have t squared. And for negative 1210 divided by 10, okay, so you have a negative 121. And with the reapplication of the square root property of equality, so you have going from t squared to t, you have plus or minus, okay, the square root of minus 121. Again, square roots of negatives will be complex numbers. So right now we have plus or minus the square root of 121 times I. And 121 is a perfect square number. So with the complex roots, we have plus or minus 11i. And then itemizing, okay, we have 11i as well as minus 11i. So again, this equation has exclusively complex roots. Now, in the case of 105, okay, we're now going from solving for t to solving for x. And in this one, okay, so we have x times, okay, the quantity of x minus 4 is equal to negative 9. Okay, now for this one you had to be careful with, okay, because you have x expressions in factored form, and there might be a temptation to treat this as if you were solving by the zero product property. Okay, but again, you have x times x minus 4 is equal to negative 9. So do not use the approach of itemizing x and x minus 4 and setting equal to negative 9, because to itemize, you want the right hand side of the equation to be 0. So we're going to have to untangle things a bit. So if we can't itemize x or x minus 4, we have to remove the parentheses. Okay, so with distributing x over the quantity of x minus 4, the left hand side becomes x squared minus 4x is equal to negative 9. So here we have a quadratic equation, and looking at expressing in standard form, so I have the x squared term on the left, and that which I have on the right I can just move. In this case, we have, upon adding 9 to both ends, we now have x squared minus 4x plus 9 is equal to 0. And with this trinomial, okay, I cannot factor into real integer coefficients. And the reason for this is that there are no factors of 9 in the real integers that will add up to negative 4. You might think of 1 and 9, negative 1, negative 9, 3 and 3, negative 3, negative 3. And none of the combinations will add up to negative 4. So we have as a recourse, we can apply the quadratic formula. So we have from x squared, you can just read it as if it were 1x squared. We have a is equal to 1. We have b is equal to negative 4. And we have that c is equal to 9. And looking at what we have with the quadratic formula. Okay, so we have a negative b, so you have the opposite sign of negative 4. And we have within the radical, okay, so you have for b squared, okay, so you have negative 4 squared. And for minus 4ac, so we have minus 4 times 1 times 9. We have all over 2 times 1. And for what we have inside the radical, so we have the square of negative 4, which will be 16 We've got negative 4 times 1 is negative 4. Negative 4 times 9 is negative 36. And 16 minus 36 is equal to negative 20. And for the square root of negative 20, so you have the square root of 20 times I. Now 20 is not a perfect square, okay, but it does have a perfect square greater than 1 that will go completely into it. And that number is going to be 4. So the square root of 20, we can factor out multiplying the square root of 4 and the square root of 5. Again, we have times I. So the reduced radical form, we have 2 times the square root of 5 times I. So we have, in the case of putting back, we're going to have for x. Okay, so you have opposite sign of negative 4 is positive. You have plus or minus. Okay, and again, we have with the radical, which we had the square root of negative 20. Okay, we have 2 times the square root of 5 times I. And we have all over 2. And if you notice, we have the leading coefficients to be even. We got 4, which is even. We got 2 in front of the square root of 5, which is even. And we have divided by 2. And we can go ahead and simplify. So we have 4 over 2 is 2. We have plus or minus. And 2 will go into 2 square root of 5i. Square root of 5i times. And just separating the terms. So we're going to have 2 plus the square root of 5 times I, also 2 minus the square root of 5 times I. Alright, so we have once again exclusively complex roots. Now, for what we have in the case of 106, okay, we're now looking at solving for D, and for this particular one, okay, so you have 6 times D to the 2/3, and we have minus 7 times D to the 1/3 minus 3 is equal to 0. Okay. Now, we don't have a quadratic equation, but we do have an equation that is quadratic in form, where we have in the variable D, okay, you have the degrees, you have 2/3 and 1/3, and the higher order, you have 2/3 relative to the lower order, which is 1/3, we come out to a 2-to-1 ratio. And so this equation is going to be quadratic in D to the 1/3. And in terms of what to do regarding the setup so as to factor, now I'll just mention this is going to run in analogous fashion to 6x squared minus 7x minus 3, at least in terms of factoring. Okay, so for this trinomial, okay, think of like D to the 2/3 is to x squared, is D to the 1/3 is to x. And if I look at factoring, okay, think of like factoring by grouping. Have 6 times negative 3. Which is going to be negative 18. Now I'm going to be looking at factors of negative 18 that will add up to negative 7, and 6 and negative 3 that would add up to positive 3. So we're looking at where we're going to have two numbers will multiply into negative 18, but that will also add up to negative 7. And guess what? Negative 9 and 2 will be such a combination. So for what we will have in this setup, okay, so you have 6x squared minus 7x minus 3. And if I take what I have with the coefficients and splitting up, so we have 6x squared minus 9x. And we have plus 2x minus 3. And we have the middle operation to be addition. So once I cross over to factoring by grouping, again we have the middle operation is going to be addition. And in looking at drawing out the greatest common factors, okay, so for 6x squared and negative 9x, we have an x shared, and also the highest number they're going to 6 and negative 9, that is going to be 3. So the greatest common factor here will be 3x. 3x into 6x squared is 2x. 3x into negative 9x, we have minus 3. Yeah, plus to be only 1. Okay, and 1 into 2x minus 3 is again 2x minus 3. So looking at what we have in the factorization. Okay, so shared in common, we have the binomial 2x minus 3. And then combining the greatest common factors and the linking operation of addition. Okay, we have 3x plus 1. Okay, now just sort of relaying this back to the original equation. So again, we have 6d to the 2/3 minus 7 times d to the 1/3 minus 3 is equal to 0. And just on a parallel course, okay, just 6x squared minus 7x minus 3 factors to 2x minus 3 and 3x plus 1. We're going to have for this equation in d. And because it is quadratic in d to the 1/3, we're going to have 2x to be represented by 2d to the 1/3. We have minus 3 and 3x, okay, that runs on a parallel course to 3 times d to the 1/3 plus 1. And we have equal to 0. And utilizing the zero product property, if I set each of the factors equal to 0, so here we have 2d to the 1/3 minus 3 is equal to 0. Also 3d to the 1/3 plus 1 is equal to 0. And itemizing the d to the 1/3, if I add 3 to both sides in the first setup and then divide by 2, so I have d to the 1/3 is equal to 3/2. Okay, so again, added 3, then divided by 2. Now, going from what we have here in d, which has right now a non-integer exponent, I can convert the power to a radical. So d to the 1/3, okay, this will be the cubic root of d. And we have the cubic root of d is equal to 3/2. And okay, so you got the cubic root of d equal to 3/2, and I can take care of the radical by raising both sides to the 3rd power. So I have the cubic root of d to the 3rd, okay, so this will be d, and for 3/2 cubed, you got the cube of 3, which is 27, cube of 2, which is 8. So you have one solution in d, which is going to be 27/8. Now for 3d to the 1/3 plus 1 equal to 0, if I itemize once again, we have 3d to the 1/3. Okay, 1 is subtracted from both ends. And then dividing by the coefficient 3, I have d to the 1/3 is equal to negative 1/3. And going from d to the 1/3 to the cubic root of d. So the cubic root of d is equal to negative 1/3. And then taking both sides and raising to the third power. Okay, so the cubic root of d cubed. Okay, so we have another d, and negative 1/3 cubed, have negative 1/3 times itself, and this will come out to negative 127. And let me pause right quickly. So again, upon converting from exponent to radical, I had the cubic root of d equal to a negative value. Had this been the square root or the fourth root or any other even root, there had been no solution. But again, odd roots of expressions can reduce to negative constants. So with odd roots, again, you do not have to worry about the principal square root rule. Okay, so we can have two solutions for d, where we have, in this case, 27/8 as well as minus 127. All right, so this completes that particular set. Now, we have crossing over into the realm of working with absolute value. Now, I think there'd be like a couple of items regarding absolute value, maybe 2 or 3 in your exam. And now for what we have in the case of 130, okay, this is about the caliber of problems you'll be looking into. Whereas 132 would be like of a whole different caliber, and I'll just say some things about that particular problem set. And for what we have in 130, okay, now we have our expression. We have the absolute value of w plus 2 followed by the additional 1 is equal to 6. Okay, so I have the absolute value term or expression as the absolute value of w plus 2. And if I get this by itself, and we have upon subtracting 1 from both sides, so I have the absolute value of w plus 2 is equal to 5. Okay. And now, so we have, in general terms, now we have the absolute value of x represented by the absolute value of w plus 2. And k, which is supposed to be a non-negative value, is going to be, in this case, positive 5. So there will be solutions for w. And, okay, so you have absolute value of x equal to k represented by the absolute value of w plus 2 is equal to 5. And again, once I remove the absolute value bars, we have w plus 2 equal to the value or values that will be at a distance of 5 units away from 0. And in this case, we have positive and negative 5. And for solving in terms of w, we have two equations whereupon we have at the lower end, we have w plus 2 is equal to negative 5, or it could be that w plus 2 is equal to 5. And taking away 2 from both sides in both equations. Okay, so it could be that w is equal to negative 7, or it could be that w is equal to 3. Okay, so we have for the possible solutions in w, we have negative 7 at the lower end and positive 3 at the upper. Now, crossing over into the threshold of dealing with inequalities and keeping the same expressions, we have for part B, we've got the absolute value of w plus 2 plus 1 is less than 6. Okay, so you have an inequality. And for what we're going to have in this particular case, if I isolate the absolute value of w plus 2 and I take away 1, we're going to have that the absolute value of w plus 2 is less than 5. Okay, and what's going to happen here, if your inequality in the absolute value is set up as being less than or equal to, it is going to be upon the removal of the absolute value bars that the expression is going to be set to the negative and the positive of that which represents k. And with our k value at 5, and upon removing the absolute value bars, we're going to have in the rewrite, okay, we're going to have that negative 5 is less than w plus 2, which in turn is going to be less than 5. And in isolating w, in this compound inequality, if I take 2 away, you have the middle is affected, and the left and right hand sides, okay, will also be affected. Okay, so we have in this setup, okay, so we have negative 5 minus 2 becomes negative 7. Negative 7 is less than w, and in turn, w is less than 3. And just for what we have in terms of, say, just a kind of a solution expressed as a sketched out graph. Okay, so we have negative 7 is less than w, is less than 3. So we have for the values involved, we have negative 7 and 3. Now the graphing solution, okay, you have negative 7 is less than w, so without the equal sign, negative 7 is not included, and from w is less than 3, again with the exclusion of the equal sign, okay, 3 is not included, so we will have an open circle or hole. And in the case of the solution set, it's going to be everything else that's going to make up the solution for what we have here. So basically for w, you have like going from like negative 6.999 all the way up to positive 2.999, but not including negative 7 or 3. And just in the case of the layout for the interval solution, so again we have between negative 7 and 3, and because neither negative 7 nor 3 will be included, we have parentheses as the only grouping symbols in the notation. As for what we have in the case of part C, now we got the same terms, and now we have this set involving the inequality, whereupon the absolute value of w plus 2 followed by the additional 1 is greater than or equal to 6. So again, we're looking at the absolute value of x, once again represented by the absolute value of w plus 2, and k again is going to be represented by 5. So we have for this setup, okay, so again, if your inequality is less than or equal to, it will be upon removal of the absolute value bars that you're going to have a compound inequality. However, if the nature of the inequality is greater than or equal to, it is going to be where upon removal of the absolute value bars, you're going to have the expression to be less than or equal to negative k at the lower end, or it could be at the upper end. We have the expression is going to be greater than or equal to that which represents positive k. So we're going to have from spinning off what we have in this statement. We have at the lower ends we have w plus 2 is going to be less than or equal to negative 5. Or it could be at the upper ends where we have that w plus 2 is greater than or equal to positive 5. And just taking what we have here. So from both of the inequalities, we have deducting 2 from both sides. We're going to have that w is less than or equal to negative 7, or that w is greater than or equal to 3. And looking at the interval notation, after we set up what we have as a graph, and I'm just again providing a visual. So we have, once again, the numbers concerned, we have negative 7 and positive 3. For w is less than or equal to negative 7, the equal sign signals that negative 7 is included. So we're going to have a close point. So we have the w is equal to negative 7 portion. And for the less than part, again, there's going to be a ray that is going to be running to the left and continuously going in the direction of negative infinity. For w is greater than or equal to 3, for the equal to portion, okay, 3 is included. So you have a close point. And for the rest, we have greater than 3. So we're going to have a ray that is going to go out to the right. And in the direction of infinity. And for what we have in the case of the interval solution, so we have at the lower ends, we have going from negative infinity, approaching and including negative 7. Okay. And the negative 7 is going to be in the bracket. And then we'll have in union with the other interval portion. So we have starting from and including 3. And again, we have going continuously out toward infinity. And again, infinities are boundless, like they're not endpoints because they don't stop. So the negative and the positive infinity remain in parentheses. All right. Now 130, kind of a challenge. Now for the case of what we have in 132, okay, this problem is, in comparison, it's going to be highly analytical. And when you get into, say, like for those of you who might be going into calculus or math 271, I think there will be something like what we refer to as like delta and epsilon formulas. And it's where you're looking at stuff like absolute value, number of lines, what is in the set, what is not in the set, very closely. And for what we have in the realm of number 132, we have distinct parts here. And we have for part A, okay, this begins with the absolute value of y followed by the subtraction of 3 is equal to negative 3. So part A begins with an absolute value equation. And just like what we did earlier with w plus 2, okay, its absolute value. The absolute value of y plus 5 we're going to isolate by moving the constant that was alongside it. So in the case of adding 3, we now have that the absolute value of y plus 5 is equal to 0. So you have the absolute value of x represented by the absolute value of y plus 5, and your k value is going to be 0. And guess what? Once I remove the absolute value bars, okay, we have that y plus 5, we have like equal to plus or minus 0. Well, guess what? 0 is not positive or negative. You might have like positive infinitesimals and negative infinitesimals, but we're not talking about this. So you have y plus 5, okay, is equal to 0. And so, because we have 0 only to work with, okay, it turns out that there's going to be only one solution for y, and that is going to be negative 5. So the only value in y that will make this equation true is going to be negative 5. Now, in the crossover to inequalities, I've had that the absolute value of y plus 5 minus 3 is less than negative 3. So once again, I have the same terms. And if I add 3 to both sides, once again, okay, we're still going to have on the left, you're going to have the absolute value of y plus 5 and we're trying to get this, okay, such that we have the absolute value of y plus 5 is less than 0. Well, guess what? Again, the absolute value of an expression cannot be negative. And guess what? Anything that is less than 0 is negative. Okay, and so this problem requires that the absolute value of y plus 5 be negative. Which it cannot be. Okay. Again, the absolute value of an expression cannot be negative. Okay, well, I have absolute value of negative 14 is positive 14. Absolute value of 14 is positive 14. Absolute value of negative 1 million is positive 1 million. And so the absolute value of an expression cannot be negative. And this is what is being asked for. Anything less than 0 is negative. So for what we have in consequence, is that for y, there is going to be no solution. Now, in the case of what we have with part C, okay, so you have same terms, different inequality. And we have in the case of part C, now we have the inequality we had to be less than or equal to. And if I add 3 to both sides, now we have that the absolute value of y plus 5 is less than or equal to 0. Okay. And I'm just going to mention, I'm going to copy this because there's a bit of a twofold situation that is involved. Okay, again, for the less than 0, that portion is not going to have a solution. But for this inequality, there's a bit of a saving grace, because even though the absolute value of y plus 5 cannot be 0, it can nonetheless be equal to 0. And so once I remove the absolute value bars from this portion, we have that y plus 5 is equal to 0, and it is from this, okay, that there is, with this inequality, okay, there is a solution that can be eked out. So you had that y is equal to negative 5. So basically part C is kind of taking a combination of parts A and B. You had the equation part where we had equal to 0, and then you have part B where it's asked to be less than 0. So part B had no solution, and the solution to C comes out to that remnant that we had worked with in part A. So we had that y is equal to negative 5. All right, and then where it gets really interesting is where we have with the greater than or equal to statements. And in the crossover, okay, to what we have in part D, it's not one I wanted. Now I'll just rewrite this. Okay, so you have the absolute value of y plus 5 minus 3 is greater than negative 3. Okay, so I'm getting the absolute value of y plus 5 by itself again upon adding 3 to both sides. So again, we have a comparison to 0 inequality. So this time we have the absolute value of y plus 5, okay, is greater than 0. And let me mention, okay, so we have just in general terms, okay, so if the absolute value of x is greater than k, then we'll have that x is less than negative k, or we have that x is greater than k. All right, so we have at the extremes now for the absolute value of y plus 5 is greater than 0. So now 0 cannot be negative or positive, but I can still branch out upon removal of the absolute value bars two distinct inequalities. Okay, so you have on a parallel to what we have with x is less than negative k. Okay, we're going to have that y plus 5 is less than 0. This is like if y plus 5 is negative, or we have y plus 5 to be positive, so we have y plus 5 is greater than 0. And looking at solving in terms of y, if I take 5 away from both sides in both inequalities, we're going to have at the extremes, okay, so we're going to have that y is less than negative 5, or we have that y is greater than -5. And in terms of what this particular scenario will look like, okay, so y is less than -5, or that y is greater than -5. Again, so for the involved value in both inequalities, okay, so you have at -5, and guess what? So for y is less than -5, okay, so we're not inclusive of -5, so we have a whole. And for the activity case, you have a ray that's going out to the left. And we have approaching -infinity. Right. Now for y is greater than -5, again, -5 is not included, so we have, once again, a hole on -5. And from this, okay, we're going to have a ray that's going to go continuously out to the right. And we have approaching infinity. And if you notice, okay, we have with the extremes, we almost have the entire real number system, and only -5 is excluded. So we have for the interval solution, now I'll do a little bit of color coding. So you have going between, once again, -infinity and -5. Then we have in union, okay, with a set of values that will be greater than -5. So you have the notation, you have parenthesis around -5, and we have going continuously out toward infinity. Okay, so once you combine, okay, you're looking at the set of all values of y such that y does not equal to -5. Okay, and so that will be your interval result in this case. Now, for the case in part E, okay, so just ever so slightly transitioning. Okay, so you have absolute value of y plus 5 minus 3 is greater than or equal to -3. And if we have that, again, just on a similar wavelength, I should say, if absolute value of x is greater than or equal to k, then we have that x is less than or equal to -k, or that x is greater than or equal to k. Right. So you have with this inequality statement, okay, so I have, once again, comparison to 0. So I have the absolute value of y plus 5 is going to be greater than or equal to 0. And so just looking at what we have in the statements, okay, so we have just like corresponding to what we have here, and with k at 0, negative and positive k will still be at 0, but we can still draw out the less than or equal to, as well as the greater than or equal to individual statements upon removal of the absolute value bars enclosing y plus 5. So we have y plus 5 is less than or equal to 0. Or it could be that y plus 5 is greater than or equal to 0. So if I isolate y, okay, so you have upon subtracting, so we're going to have here, okay, so you have that y is less than or equal to -5, or we have that y is greater than or equal to -5. And so we have in the setup, okay, this time 5 is going to be included. I say -5 will be included. Alright, so for y is less than or equal to -5, okay, the equal sign signals that we're going to have a close point on -5, and once again there will be a ray that's going to go continuously to the left. We have approaching -infinity, and as for y is greater than or equal to -5, again you have like a close point. And we have a ray that's going to go continuously out to the right. So we have everything contained in -5 is included. And just kind of give you a little idea of what's going to happen here. So you have for y is less than or equal to -5. So we have starting from -infinity, and we have approaching and including -5, and the -5, okay, we have bracketed, and then we have in union, okay, and we have going from and including -5, okay, and we have once again approaching infinity. Okay, so for what we have here, if you notice, for both sections, okay, -5 is included. We have indicated by the brackets. Okay, so because of the brackets, think of it kind of like -5 because it is a bracket. Okay, think of it kind of like the brackets as kind of like a seal that bonds the sections together. So you can say that the pieces will fit together. And so for the interval solution on this one, instead of two separate sections, we're able to unite together, and so we're going to have the solution is going to be the set of all real numbers. So you have going from negative to positive infinity. So you have a set of all real numbers in the mix. All right, and now I know that there's in Alex, okay, section 1.3, okay, which is not going to be in your first test. Okay, that set of exercises is already available, and I'm going to make an adjustment, okay, to the due date. And I just want to give Okay, just a little bit of a mini lesson. Okay, for what we have from this particular section. Not so much in terms of equations, but just kind of more along the lines of the concept of what defines a function. And again, I'm just going to give you a bit of a mini lesson, okay, with functions. Now we have with functions, now a function is going to be a mathematical relation. We're in the xy coordinate system. Okay, we have that for each x value, there's going to be one and only one corresponding y value. And I'll just kind of put emphasis on this, okay, one and only one. And regarding the xy coordinate system, okay, now for ordered points, or I should say for all points, and points also regarded as ordered pairs in the xy coordinate system, you have to be of the form x and y. Okay, and in terms of what is referred to as x, okay, x is going to be the independent or input variable. And for what we have in the case of y, okay, y is going to be referred to as the dependent or output variable. So in other words, it's kind of like the output or the end result is, in terms of how it ends up, okay, it's going to be contingent upon how things begin or what is put into the system or situation. And now, for examples of functions that we have regarding x and y values. Okay, now functions can be given in the form of graphs or equations, but I'm going to just kind of present what we have in functions as sets of ordered pairs. Okay, we can have just like an example of functions, and we can say we have like 0, 2, 3, 5, and -1, 9. Okay, And this is going to be a function. And the reason for this is that we have, again, for each x value, there's going to be only one corresponding y value. And so we have the x value of 0, that is paired up only with 2. For the x value of 3, that is paired up only with 5. And the x value -1 is paired up only with 9. Okay. And just some of the features we have, and this term domain you'll be seeing quite a bit throughout the course. And domain, you're looking at the set of x values. And for the domain, okay, if I express as a set, so the domain you have 0, 3, and -1. And you can write those values in the order that you see them. But if you had like a problem and you looked at the back of the book and you noticed that you have a different sequence of the values, very likely you're just going to see the numbers in order from smallest to largest. So it doesn't matter what order you write the values. If you have like 30, -1, or -130, it's still going to be the domain. And for what we have in the case of the range, range is going to be the set of y values. And for the y values case, they have 2, 5, and 9. It could be 592, 925, as long as you got those 3 values in the set. Now, another case of what we have regarding functions. Let's say we have -1, 1, 0, 5, 3, 9, as well as 4, -6. Okay, this is also going to be a function. You have the x values. You have -1 is paired up only with 1. And we have 0 is paired up only with 5. The next x value, 3, is paired up only with 9. And then we have the last of the x values, which have 4, is paired up only with -6. So we have, in the case of the domain, just lining up the x values. So we have -1, 0, 3, and 4. As for what we have in the case of the range, okay, so you got 1, 5, 9, 1, 5, 9, and -6. Okay, and again, you could reorder this from smallest to largest. So you have -6, 1, 5, and 9. Now for the remaining portion, and this will be kind of like something akin to separating the wheat from the chaff. Okay, and so we're looking at whether the set of ordered pairs will be a function or not. And we'll say in the first case, right? Say we got say you have -1, 1, and we have 3, 4, and we have 5, 7. Again, for a function for each x value, it must be paired up with only one corresponding y value. So we have -1 paired up only with 1. So far, so good. 3 paired up only with 4. And we have 5 paired up only with 7. So this is going to be a function. And again, just for the domain. Okay, so we have the x values. So we have -1, 3, and 5. As for the range, Okay, so you have 1, 4, and 7. And let's say that if I have negative 1, 1, 3, 4, 5, 7. Now I have, let's say, 3, 10. Okay. All right, so I have negative 1, 1, 3, 4, 5, 7 show up again. But we have one more order pair with 3, 10. And guess what? That x value 3 repeats. And it repeats with a different y value. So you have the same x and a different y. And because of this, this set of order pairs is not going to be a function. Now, let's say if we have like order pairs, say we have 0, 1, 1, 1, 2, 1, and 3, 1. Okay. Now again, to be a function for each x value, there must be only one corresponding y value. Okay. Now we have with 0, 0 is paired up only with 1. Guess what? As an x value, 1 is still paired up only with 1. 2 is paired up only with 1. 3 is paired up only with 1. So this is going to be a case of a function. Now if I switch the order of the coordinates, so we have 1, 0, 1, 1, 1, 2, and 1, 3. Guess what? You have 1 keeps appearing as an x value, and with each reappearance you have a different y value. And so because of this, okay, this set is not going to be a function. Okay, now let's say if we have as a little bit of a tiebreaker, whether we have a function or not. Let's say we have like 1, 2, 3, 4, 5, 6, 3, 4, and 7, 8. Okay, now for the easy parts, okay, now we have 1 to appear once as an x value, and so that appears only with 2. 5 appears once, and that is uniquely paired up with 6. 7 appears once, and it appears only with a y value of 8. Now in the case of 3, okay, 3 is paired up with 4, and 3 is still going to be paired up with 4. Okay, so a point can repeat in a function as long as that x value appears only with the original y value. Okay, so you got 1, 2, 3, 4, 5, 6, 3, 4, and again 3 is uniquely paired up with 4, and again 7 is uniquely paired up with 8. So this is going to be a function. And just touching upon, see, with these functions in 3 and 5. Okay, now for your domain, again you have your set of x values, which will be 0, 1, 2, and 3. As for the range, guess what? You got 1, 1, 1, and 1. And if you have repeating elements, you don't have to put them down. So for the range, you have just the number 1, and you don't have to repeat elements. Okay, so you have just the number 1 for the range. And for this last case here, for the domain, okay, so we've got the x values. So you have 1, 3, 5. 3 is already in the mix in spite of repeating, and then we have the number 7. Now as for the range, okay, so you got 2, 4, 6. Again, 4 is already present. And we have finally the number 8. Have with the first test, okay, this will be available later today at 12. And again, there will be a 90-minute time limit, and it must be completed in one sitting. And okay, and it's okay. So again, it must be completed in one sitting. So so just be where you can will be uninterrupted, for 90 minutes, or however much time you need. And once again, the deadline for submitting this exam will be Monday evening at 11:59 p.m.